Okay, welcome to our next paper club. Today, we are going to talk about a very interesting paper, which is ML-wise quite simple actually, but the application is very intriguing because it's from physics. And the idea is that we can use a very simple deep learning model to learn very complex physical behaviors. I'll go into details just in a moment, but for now, let's introduce the paper. This one is called Newton versus the Machine, already a very intriguing title. So Newton, because the problem they are solving has been introduced by Newton, or actually, it was introduced by Newton as far as I understand, based on his Newtonian mechanics equations. So basically, we have three objects which affect each other in using their gravitational fields. Sounds like a simple problem, but actually, perhaps surprisingly, it's really difficult to compute trajectories of each of these objects. And there have been many attempts, most of them unsuccessful, until very recently there was a new solver that could compute the integrals that arise from these equations by basically doing simulations from several different starting points and then averaging the results. Okay. What they do here in this paper is train a neural network that can learn from simulations and then predict without actually having to run any simulations. Okay, so let's go into details here. But before that, any questions, any comments about the paper, about what I said? Okay, cool. Right. So first thing I actually liked about this paper was that they cite one of Newton's original works from 1687. Perhaps the oldest citation I've seen in an ML paper. So the idea is that, as I said, we have three objects, gravitational objects that affect each other's trajectories. For an example, we have a few examples here later down the paper. So you can see those are just three objects, green, blue, and red, and they move around each other. The funny thing is that these can be very random, right? Not random, but chaotic. Chaotic in a sense that if you move their starting positions just slightly, the trajectories get affected by a huge amount. This is what makes the problem unsolvable. Okay. Another interesting thing from the abstract is that, again, you don't see this regularly. Here they claim that they improve, here, let me find the abstract. They improve, they speed up the computational cost by 100 million times. It's a very big claim, right? You don't usually see these kind of improvements, but well, it happens. So there is a bit of, we start with an introduction to the problem, a bit of history of attempts to solve. And the most successful one was a solver proposed, which we actually discussed in the appendix. There was a solver that basically does an ensemble of simulations and then averages the results. And we are going to use that solver for our training set. But before we get there, let's actually talk about the problem setting, because they also make a few assumptions, right? So this paper solves the three-body problem under certain assumptions. I think that's also perhaps important, because first they make an assumption about symmetry, saying that if we know the positions of the two objects, x1, x2, you can see here, the third object can be computed by using those two positions. Okay? So this actually kind of simplifies the problem, but I'm not entirely sure by how much.
I mean, isn't it just like a momentum or center of gravity conservation? So it's an exact thing, not really an assumption.
Yeah, exactly. I thought that's actually not a limitation, but at the end of the paper, the discussion, they mentioned that they want to further study this problem without assumptions.
So essentially saying that the masses might be different, right? So here the assumption is that all the masses are the same, right?
Maybe that's what makes a difference. Yeah, that's true. Yeah. Yeah, we'll get into that in a moment, but yeah. Because yeah, that is right. It is the assumption is that the mass is the same. Yeah. Okay. Shall we continue? So the method is basically a neural network that's trained on simulated data. Simulated data, which is collected by having x1, x2, x3, 3 points with initial positions. X1 has the 1, 0, x2, x3 are randomly situated somewhere in the unit semicircle in the negative x-axis. So the starting points are kind of controlled, but there is also randomness. Right? They make it on the same plane, but randomly positioned. So this randomness allows us to run simulations and generate enough data for the training set. Okay, no comments here, I guess. And the neural network is actually a straightforward neural network, fairly simple one. I think only 10 layers. Define the size. 10 layers, about 100 something neurons in each layer. And they run 10,000 simulations. They split into training and validation sets. And then basically normal stuff, right? Usual split, and then they use the Brutus is the solver I mentioned earlier. This is the solver they use. They use for generating the training set. So there's a question. I'm not sure why they asked why they chose the architecture they did. Nope, they just chose a simple one. I think that there may be a bit of hyperparameter tuning, but this is really the first thing you try, right? I guess the depth and they did a bit of a discussion in terms of the optimizer of choice and a few other parameters. And they said that they used the best ones they found. So they chose Adam because it was the best. But also they also said that they played with hyperparameters a little bit, but there was no big difference. In terms of overall architecture, I guess they just chose the simplest one, right? First work, first attempt. So they went for the simplest architecture. Cool. Right, there is another hyperparameter to choose, which is for the Brutus solver. So Brutus takes an epsilon for the accuracy and something called the length of words. They also said those two. So the epsilon is actually very small here for the training set. Other than that, there really isn't much else in terms of the model architecture here. Yeah, they mentioned Adam, I think 10 or 20 epochs, fairly usual. And let's look at the training curves, maybe. Actually, well, there is they made the plot for the architecture. So the inputs are the initial position of x1, and I think, and the time t, right? For how long you want to simulate, and then the output becomes the positions of x1 and x2, and x3 can be computed from those two because of the gravity, because of the symmetry from gravity. Okay, they made a nice plot with Newton's portrait here. On the other plot, here we have the training curves, right? They took 1,000 epochs. I think actually, if you look here, it's 10,000 pulses with 5,000 brush size. So I'm not entirely sure what the 1,000 epoch here means. Maybe only for this one experiment. But anyway, so they try with these taus represent how big the training set is, right? So
I thought that is the
yeah.
time they're trying to predict forward, right?
Yes. The best.
They put, I think, that the time to be unitless, so time is just a number. And I think the idea was, if you look at the picture, right, that the algorithm has generally a harder time predicting things that are further into the future, which makes sense because this is like a chaotic system. So they do mention at some point this Lyapunov exponent, which essentially says how quickly does your system move very far from your starting position if you have a very small change. And but they didn't actually do much about that, like test out whether these errors are correlated. But you would think they are.
Yeah. So there is one interesting thing here, because they say the blue line t under 10 is the entire data set. What does it mean then?
I think what they did is they have these 2,561 data points they simulate with their Bluetooth method, and then they cut it arbitrarily short, and essentially build a training model only on the first 1,000 labels and then the next 2,000. So which essentially means that you go forward in time a bit more, and you extend your horizon, and clearly
so after each solution they make the result and input for the next simulation.
Actually, I'm not sure whether they try to predict all the way I got it is I thought they predict the whole trajectory. So they predict for each of the next 1,000 points, they predict what is the XY position or coordinates of these. But I'm actually not sure whether they predict only the very last point or all of them. Because if it's all points, you would expect also that the mean absolute error goes up, right? Because you have more points on which you. I know it's a mean error. Never mind, that was stupid.
Yeah, there is another strange thing. So if blue, right? That's the tiny blue is all data. Why is there any difference between the training and the validation errors?
Because it's you have more points and times that are further away from your starting point, so you have more time for your chaotic behavior to have sort of kicked in and moved the trajectory away from where you would expect it to be.
Right. Oh, so this entire data set is a bit confusing, because so it's farther ahead in time, so there is a bigger discrepancy. Makes sense that makes sense, right? And the red one is much tighter with smaller errors.
Mhm.
But then I don't understand why is it called entire data set?
I think it's more like the entire target set. I think the number of
Yeah.
training samples is always the same, but it's it's essentially how far forward do you predict.
Oh, it says how many labels per simulation.
Yeah.
Right. So they have more labels per simulation.
Yeah, exactly. So
Yeah.
essentially saying they go, rather than predicting only the first 3.9 seconds, they predicted next 10 seconds or whatever units they chose.
Okay, that makes sense. Cool. Any other comments here? Okay, there are a few examples from trainings and validation sets showing that they can be actually very different. This one is suspiciously symmetric, but
That actually is also quite interesting in terms of these chaotic problems, right? So that if you measure in space, so this Lyapunov exponent, it didn't explain actually what it is. It's actually quite a nice concept. The idea is, right, that you have essentially what you're trying to do is you solve a differential equation system, which is smooth because it's only second order. It's all classical mechanics. It's all fine. So you know that neighboring solutions must lie close to each other, right? So if you move your point just a little bit to the side, then at least on some time horizon, you shouldn't stray away too far from the original solution, just because there is not enough time in a smooth system to do that. And exactly how far you can stray away, that is essentially what the Lyapunov exponent tells you. Now it turns out that locally, these exponents can also vary in space. Like the solution on the right lower panel is probably one solution where actually it's barely chaotic at all. If you move solutions maybe close by, you would always get something that is semi-periodically and only in a very, very, very long time scale that might actually move about to be random or quasi-random. And that would be quite interesting if they would have checked that. Is my solution where you have locally something that looks like very normal behavior, is my test error there better than at points where, like the upper left, where it gets very, very quasi-random very, very quickly?
That's very interesting. Yeah.
I think as well, I mean, I think what's not clear here is that these results appear to be too good for me. I know we've got the training errors above, but these seem to be absolutely bang on. And when you look at the mean average error, they're still quite large for the scale, I think. And when you look at those graphs that they're plotting, they're saying that they can predict it to arbitrarily high accuracy. And I'm not questioning, I'm just curious. That to me seems too good.
That is only for the short times, right? So the lower panels was only for the 3.9 seconds or 3.9 time units forward prediction. It's quite possible, I think, if depends on how dense your simulation data is, right? So if you have a training set that is very, very dense in this region, I could imagine that it becomes quite smooth, especially since it's a smooth problem. But yeah.
Yeah, but like when there's discontinuities, like when there's sharp turns, I mean, we don't know how dense it is, right? They don't give any indication. They just joined it all up and made it look like continuous. Yeah. So yeah, I don't know quite what we're looking at.
Yeah, technically it shouldn't be ever really sharp turns, right? Because I don't think the balls are allowed to crash into each other because they are essentially infinitely small, right? So you would expect, even if there's a relatively sharp turn, it's still locally nice and smooth, actually, if you get to zoom in quite closely. Yeah, I don't know. It looks very good, but again, if you don't know how many samples they actually used around that in order to train it, it becomes very, very hard to say that whether the machine actually learned anything about the nature of the thing.
There is one case when when the error actually can get very large. They talk about it at the end.
Yeah.
That's when the two objects get too close to each other, and then it's they affect each other gravitationally in a weird way, and the errors can get large.
Yeah, it was
So
also, I
they
think, relative energy error, right? I think because you know in such a system energy must be conserved, and if
but the
yeah.
training error is still low then. That's actually the loss is still low.
I think they said after they do the energy projection, so finding the closest positional arrangement to their solution that still fulfills energy conservation, they get much better results, which is what you would expect. I think it's
yeah, they had to project on to force energy preservation by adding projections to force that energy preserves, which makes sense, I think. Yeah. Okay.
The question is almost what do you do with this in practice, right? So when they say yes, you speed up training inference time so much, but I would think you would need quite a lot of prepayment in order to like do the simulations to train your problem on in order to do it right. I would be very surprised if this would extrapolate at all.
I think they mentioned in the paper that they did use novel data in the test data, right? That wasn't seen by the network before. So there was something there, I think they found.
Yeah, but that must have been very well embedded in their original training set, right? So the points were novel, but they were probably infinitesimally close to any other point that they already trained on, I would think.
Yeah, that was my sense.
How many points they have trained?
It says for 10 days. I think it says 10 days. Let me find the actual. I think they said that they run simulations for 10 days, which is what they use for 10 days, right? I think this data for 10 days of computing time, which is 10 to the power of 5 time points. So 2,500 discrete time points, which multiplies to 10,000 time points, or 100,000 time points.
Yeah, so that would be if they say 2,500 roughly for their maximal length per path. It's actually not too many paths, right? It's roughly then 100 paths. I don't know, that seems also quite low then actually.
I mean, if it takes only 10 days to train it, and then you never have to spend any time on a three-body object trajectory computations, it seems fair, right?
Well, as long as whatever you're interested in has the same mass and is in the starting point between 0 and 1 for each of those coordinates, then yes.
Yeah, well, since we are talking about it, I actually checked if there has been further work after this, because this was published in 2019. So I was thinking, has anyone actually tried to generalize the solution? But I didn't find anything. So maybe once you break the symmetry, it's much harder to solve, to train.
Yeah, or to generalize. That is say, right? So the training set was 9,900 paths.
Yeah. Simulations. So 9,900. Oh, but also the validation set is actually very small. Normally you would see a 80-20 or something like that.
Yeah.
So yeah, there's a couple of comments there. So given that the training set, the data set is quite small, they've chosen quite a relatively rich architecture, right? So when you look at the architecture that they've used, it's like 10 is deep 128 nodes. I mean, that's huge, and they're saying that they've managed to get something bang on. They make it sound trivial. I'm not sure that that's necessarily the case. I would have expected this to be, to provide lots of solutions that were absolute, that wouldn't have worked.
Yeah, that's a good point. Maybe they didn't even try with smaller models. Who knows?
Yeah. Because what they said that they want to use that to investigate star formations, or I doubt that because the restrictions on which they train that are quite limited. So if you have already that training data, you probably would have been already calculating the star stuff that directly.
Yep, fair. Should we continue?
Sure.
Sure.
Nice. Right, so I mentioned this briefly, but basically what they add is the special case to preserve energy, because in the system the energy must be preserved, but there are some cases when it doesn't. That happens when the objects are too close to each other, and the model wasn't able to learn that well enough, and the error actually gets quite large. So they did a projection step, and they actually plotted the energy error graph. So Brutus is the state of the art. That's what they use to generate the training data. And they also compare the projection. The green one is the projection, which is still slightly worse than Brutus, but close enough, I guess. And this other one has some spikes here, as you can see. But overall, it's not too bad without projection. I think that's all really. There is an appendix where we can look at the problem formulation. There's the error that's the error they compute, and how they define the projection layer, which is basically an optimization problem. There's the energy error, or regularized with these distance constraints, so that we don't change we basically minimize, actually project, right? Minimize the distance when you project, which is a only 2 variable problem really. So they solved it using gradient free method. Other than that, I guess I like this paper because the whole idea of you have a too difficult problem, too computationally expensive problem. Why not run a few simulations and train your model to learn to sample, right? That was the interesting part for me, which I didn't think about before. And maybe it can work in some cases.
It would be quite cool if they would have used also the velocities. I think right at the very beginning, you always assume that the 3 points are essentially static. Right? So they start out not moving, and then slowly gravity is pulling them together and starts to move them. And they use that, I think, to do the prediction, right? And in the Brutus solver, I think they have to use velocities, otherwise you can't really forward it. Would be interesting what happens if you add this information to the training set and let them predict the velocity as well, and test on it. It probably would even improve the performance at essentially no additional cost, I would think.
Yeah, that's actually good. Yeah, that's a good shout. There is a comment. They also use neural networks on light diffusion models, I reckon. I'm not sure what's a light diffusion model.
Is it electromagnetic light diffusing, or yeah?
Yeah. Is it also a chaotic system? Maybe.
It can be. I think that it depends on where it diffuses to. There is actually some really interesting research on wave breaking in random materials, and so I did my master's on that. It was because they show that certain electromagnetic waves or particle waves actually become fractals, which is really quite cool. And that's where a lot of these kind of diffusion stuff can also become anomalous, where the diffusion behaves very, very different than in free space. But sorry, that's a bit far out.
So can I ask a question?
Of course.
So are they claiming that they've got an analytic solution, at least for a very small subset of the three-body problem? Or
Well,
is it that they're just showing that they can replicate a simulation? Because there has to be some claim to knowledge at some point. And I suppose it's more general, to your point.
Well, how do you define an analytic solution? I mean, I guess we can write the neural network as an analytic and as a function, right? Because we know the weights.
Yeah,
Probably.
exactly. But how much of that is knowledge? How much of that is just a very complicated equation that denies tractability because, you know, we're humans?
Yeah, you could argue it's a fairly complicated numerical approximation procedure that looks like a function. Yeah, I don't know. It's a good point, actually.
Or actually, no, it's not analytic. It's an approximate solution, right? There is an error, even compared to another numerical solver. So it's still an approximate function.
Yeah, I suppose when I read this paper, I was wondering, are they paving the way to say there are analytic solutions or an analytic solution that could solve this? Or is this just another tool that you could use in numerical methods to look at this issue? And I think it's something more than just numerical methods, I think.
It's more of it's a numerical solution to an integral, right? Because computing the integral is the complex part. So if you could say the integral is the analytical solution itself, right? But computing that integral with certain robustness is the actual difficulty. So what they do is have a better learned sampling to compute the integral. That's how I see
it. I think you can prove, right, that there is no analytical solutions. You can only approximate it, and of course the error grows as further you are trying to approximate this. I think we even mentioned at some point that there is some analytical function.
Yeah, I want to scroll back, find it, because it's funny that they mentioned that the requirement to hold floating points grows exponentially, and there was actually a specific number somewhere here, which is a problem for numerical solvers. That's why this Brutus solver was invented, which basically does an ensemble of solutions and averages them. And it's able to do it requiring less memory.
I wonder why does the solver need to be averaging in the first place if it's more or less integrating the equations of motions directly?
I think it's because of the starting positions, right? Because it's a chaotic system. In the initial, it solves with different initial positions and averages. That's how I interpret it. I mean,
so you're essentially saying you don't know your starting positions, even hypothetically, exactly?
Something like that, I would say. But there is a push. Maybe it could be useful even if one cannot really trust their predictions in using their predictions as an initial guess for an iterative solver for this type. Yeah, exactly. Yeah, because you can use it maybe as a good initial guess. Yeah.
Would be quite interesting to think about at what point do you have a system, even if it's approximate, that you would actually use for research on something you don't know the answer to.
As in there is no ground truth, but you trust it so much, you just use it.
Yeah.
I mean, the thing there is that, you know, are you sure your sampling is adequate to cover all the cases that you need? I'm not sure in this paper, I'm convinced that they covered everything. That would describe it fully, but I could be wrong. But I think, Arvind, that's one of the things about, you know, what point do you use it? I mean, I think it comes down to, in part, it has to be answered by how complete is your sample.
Yeah.
Initially. That's what I would do anyway. I'd want to be convinced that I've got a really, really rich, you know, set to train it on.
Any other comments? Okay, then thanks. So I'll stop recording.